Imagine you have a field of energy where the material isn't spread out evenly. Instead, it gets progressively thicker and heavier the further you move away from the center point. This project is a fascinating exploration of a simple yet profound question. If you place different containers into this field, which one will capture the most material? Here is the story of how that question is answered. The geometry of mass. The core realization of the project is that the shape of the container matters more than its overall size. When you place a cube and a sphere into this field, they interact with the space around them in very different ways. The cube has flat faces that keep a significant portion of its volume relatively close to the center, where the material is thin. A sphere, however, expands outward toward the edges. Because the material becomes significantly denser the further you travel from the origin, the sphere's rounded geometry acts like a massive scoop, pulling in far more mass than the cube, even if their volumes are similar. The rule of the outer rim. The study pushes this concept further, looking at more complex forms like stretched-out ellipsoids and donut-shaped toruses. Through these experiments, a clear pattern emerges. The outer rim holds the key to mass accumulation. In every geometric shape tested, the total mass is heavily dictated by the boundaries. The parts of the object that can reach the farthest from the center are the ones that glow with the most mass. By calculating the contents of these shapes, the project demonstrates that mass isn't just about volume. It's about where that volume sits in relation to the center of the density field. From math to visualization. This project is more than just a theoretical proof. It is a rigorous, step-by-step journey from abstract logic to visual reality. The foundation. It begins with analytical proofs that define the laws of the density field, establishing the ground truth for how matter clusters. The workflow. Using detailed flowcharts and state diagrams, the project outlines the progression from these equations into a functional digital workshop. The digital lab. Using Python, the project transforms those dry calculations into vibrant 3D models. You can see the density distribution in action, where cool, dark colors represent the sparse center, and bright, intense colors illustrate the heavy accumulation at the outer edges. Ultimately, this work serves as a practical bridge between the invisible world of calculus and the visual world of computer graphics. It shows that whether you are dealing with a simple box or a complex manifold, the shape of the container is the primary architect of what it holds.